right. These notes are should be a review for most of you. If you came up to AP Calc from CP pre-calculus, then you might not have seen polar curves before. But I think that it's not too hard. Polar curves are often presented in this sort of, well, in the context of a pre-calculus course where you're doing all these seemingly unrelated things. Might seem like this isolated topic of weirdness. But polar curves are pretty cool, and our mantra when we're doing polar stuff is that you have to think polar. So the very, very basics are, we are so biased because of our math training that the way you locate something in two-dimensional space is by an ordered pair, a point that you might call x comma y. And that's how we think. All of our functions rely on this idea that f of x or y equals some kind of function of x, and that tells us for any x value that we plug into the function, this is the y value that goes with it, and we draw curves to represent those sets of ordered pairs, and we're pretty comfortable with that. But that's not the only way to do it. That's by it I mean that's not the only way to locate a point in two-dimensional space. Of course, we understand that anytime we are locating a point in two-dimensional space, we have to choose an origin. Right? So if I tell you go over x and up y, you need to know from where. And when we draw our axes here, from where is the origin, right? That's from the point 0, 0. You go from 0, 0 over x and up y. That's the kind of thing that's so maybe obvious in some ways, but it's worth reflecting on a little bit. Sometimes we get so caught up in the mechanics, the procedural aspects of working with functions and things like that, that we kind of lose sight of what we're really doing and what these ordered pairs are. But anyway, I wouldn't get off philosophical. Not yet, anyway. So here's another way to do it. Instead of saying, if you were giving directions, instead of saying to get from here to here, which is really what we're doing, go over x and up y. Go over x and go up y. Instead of doing that, we could say from the origin, point yourself in the right direction, and to describe that direction, we could use an angle, theta, right? So in other words, we understand that this would be the 0 direction. So turn counterclockwise through this many radians, so you're pointed in the right direction, and then go this far. Right? And if you were just trying to get from here to here, you might actually appreciate these directions more, right? You might appreciate, instead of somebody telling you, walk 20 paces this way, or how about 30 paces this way, and 50 paces this way, or 40, sorry, I'm trying to make it nice numbers. Say if 30 this way and 40 this way, they could just point you in the right direction and say, walk 50 paces this way. It would save you 20 paces overall, right? The shortest distance between 2 points, after all, is a straight line. So, that should give us some appreciation for what polar coordinates are, right? So, what they are, no pun intended there, sorry. So, you could describe a point xy, of course, or you could give that angle theta and then the r. We usually do them in this order. It kind of makes sense that they would be in this order, that you can't tell the person how far to go and then tell them the direction. You got to tell them the direction first and then how far. So could do it this way. And there's some obvious trig relationships between these two different ways. So we'll just talk about those real quick. You can see them all here, I'm sure. So the if you want to go from xy to theta r, then, well, let's see, how would you get a theta from this information here? Now, that means in other words, you're given xy and you want to know what theta is. So you can't use r. We don't know what r is. We know what x and y are. So theta in terms of x and y would be, well, let's see, tangent of theta is equal to opposite over adjacent. So tangent theta equals y over x, which means theta is the tangent inverse of y over x. We do that in physics all the time, right, to find that angle. So nothing new there. And if you wanted to know what the r was, well, by the Pythagorean theorem, x squared plus y squared equals r squared. So r would just be the square root of x squared plus y squared. So that's how you could turn an xy point into a theta r, by doing this. How about the other way? What if you knew theta and r, and you wanted to turn it into an x and a y? Well, it's a more basic trig there. So let's see, what would x be equal to? Now I have to give my answer here. I want it in terms of r and theta. So let's see. The trig function that relates theta, x, and r is the cosine function. So cosine of theta would be equal to x over r, or in other words, x is equal to r cosine theta, and likewise y is equal to r sine theta. Again, we do that in physics all the time, basically breaking a vector up into its components. That's equivalent to what we just did there. These moves here are going to be very important for us when we start doing calculus with polar functions. So keep that in mind especially. This we know, I mean all of this we know, it's basic right triangle trigonometry, but this will be especially important. We'll talk about that, probably not in this video, in the next video. Okay, so what about polar curves? Just like we describe curves when we have Cartesian coordinates, or x's and y's, we say y equals, and then some stuff happening to x. We do them with polar curves, we say r equals some stuff happening to theta. So I'll just do a couple quick examples here. How about r equals cosine theta? What would that look like? So this is where I'm going to invoke the mantra here, think polar. So you think here, you start out by looking in the direction theta equals 0, and you figure out what the r is. And then as you turn through all those different angles and try plugging in all those different angles, the r changes. So in the same way that you would like draw a circle with a compass, it's like you're drawing a curve here, but the r is changing. It depends on what that angle is. So it might get shorter as you turn, or it might get longer as you turn, or it might do all sorts of funky things as you turn. But what you want to imagine is you're sort of standing here at the origin looking out in all these different directions, and for every one of them, that value of r might be something different depending on how the function is defined here, or how the polar curve, I should say rather. These are often not what we would call a function. Okay, so how would we do this? We could imagine here, I'll just do a quick table. I'm not going to do too many values. But just like we would make an xy table, I'm going to make a theta r table. So when I plug in 0, cosine of 0 is 1. When I plug in, let's see, what's another kind of nice thing I could plug in? How about when I plug in pi over 3? That's a nice one for the cosine function. Then the r is 1/2. When I plug in pi over 2, the r is down to 0. And if I go up to 2 pi over 3, then the r is negative 1/2. I'll have to talk about what that means in a second. And then if I go all the way up to pi, then it's negative 1. And let's just do that so far and see what that looks like. So this means I start here, I look at 0 radians, and I get a point at 1. And I should be careful here. There isn't necessarily a point there. That's looks like a point because I've been dotting there. But all right. And if I look at pi over 3, right, which is about 60 degrees, not about 60 degrees, it is 60 degrees, then it's 1/2. So that's about maybe here or so. So think about what happened to get from here to here. It's going from 1 down to 1/2. So it's like our compass is getting a little tighter there. And then if I plug in pi over 2, in other words, if I look straight up, then I get a point at 0. And it's really important to note here that I'm getting a point here not because the angle's 0, but because the r is 0. So if you see a polar curve that goes through the origin, it doesn't mean that it was at the point 0, 0. It just means that for some r, for some theta value, you got an r of 0. All right, and then as I look off this way now to 2 pi over 3, which is 120 degrees, that says I have an r of negative 1/2. So I'm looking this way, but my r is negative. So that means I plot the point behind. If I imagine you're looking this way, that negative r means you plot it back here behind you. And then when I look at the direction pi, I get an r of negative 1, so that means behind me 1. So this is what happens. Oops. And notice that this thing does kind of have a direction, right? Like it came around this way. And notice also this does happen to be a circle. And notice that it repeated. It was a full circle from theta equals 0 to pi. I didn't have to go all the way around to 2 pi to get it because of those negative r values. I got the whole circle just looking from 0 to pi because once I got past pi over 2, I was looking behind me. We're not going to do a whole lot of this. You probably did some in pre-calculus. But you could, if you really want to prove to yourself that that's a circle, you could take this and change it into x's and y's. So I'll just do that real quick so you believe me that it's a circle. And you just maybe remember that you can do this. Proof that r equals cosine theta is a circle. And we could, furthermore, we could actually do some analytic geometry and say, well, let's see, it looks like the center's at 1/2 and the radius is 1/2, right? Center's at 1/2 comma 0. So I could like write that out and anticipate what I should get here. I'll leave that for you to think about, and we'll get the result here. So if we start with r equals cosine theta, I want to turn everything into x's and y's. Well, r is equal to x squared plus y squared, the square root of that, and cosine theta is equal to x over r. Sorry, I can't have an r in there, can I? So let's see. So I have to do x over r, but r is this. X squared plus y squared, square root of that. That's a little messy, so cross multiply there. The two square roots will cancel each other out. So x squared plus y squared equals x. Now that is that circle, but maybe it's not as clear in this form, so we could try to get it into standard form. X squared minus x, and then plus y squared equals 0 on this side. And to get it into standard form, I would have to complete the square here. So that means I take half of this, which would be half that coefficient, and square it. And if I add that to this side, I have to also add it here. And then the reason we complete the square like that is because now that's a perfect square. You can FOIL that out and check that if you want, if you're a little rusty with that. Equals 1/4. And I'm going to write that as 1/2 squared. So there you go. Now we've got a circle in standard form where we have the center is at 1/2 comma 0 and the radius is 1/2, which is exactly what we have here. And I think you could also make a case, I don't think I have to try too hard to convince you, that this equation for the circle is quite a bit nicer than this equation for the circle. So polar might be, well, it is kind of, it's certainly less familiar than Cartesian coordinates, but there's lots of situations where polar versions of curves are just nicer to deal with than their Cartesian equivalents. All right. Couple more quick examples of what the curves look like. Here's a really easy one. How about the polar curve r equals 2? Notice that there's no thetas here. The r is just a constant. What does that mean? Well, since there's no thetas over here, just like with a horizontal line, y equals 2, that's kind of like saying y is 2 regardless of what x is. Y is just 2. So if you're graphing a horizontal line, it means you go over x equals whatever, and you always go up 2. You just get a horizontal line at 2. The y value is always 2. So here the r value is always 2. So regardless of what direction I look in, I always have a radius of 2, or an r of 2. Kind of think about the r like it's r for radius. Or a position vector from physics, that works too. So you just get a circle of radius 2. And again, you could easily make the case that that's nicer than having to write out the equation for the circle, x squared plus y squared equals 4. Not that that's horrible or anything, but that's very simple, and it's very suggestive of what it is. There's all sorts of examples we could do. Let's think about one. What would it be? We had r equals, how about 2 cosine theta plus 1. What if you do something like that? And I'm just going to sketch this. I'm not going to make the table. I'm just going to kind of do it freehand here. We'll see how that goes. So notice here when I plug in 0, I get, well, you could think about this first of all. The cosine function oscillates between 1 and -1, right? So the biggest this is going to be is 2, and the smallest it will be is -2, right? Because this is like a cosine function with an amplitude of 2. So it's going to go up to 2, down to -2. I'm adding 1 to all those values. So that means the value of the r is going to go from a maximum of 3 to a minimum of -1. So when I start looking this way, that's at 0. So the r is 2 times cosine of 0 is 1, so 2 plus 1 is 3. Right? And then I go through my some nice values. If I wanted to try, say, pi over 3, then cosine of pi over 3 is 1/2. 2 times 1/2 is 1, plus 1 is 2. So when I'm looking out in this direction, I go out about 2. I'm just kind of, that might be a little too far, but something like that. When I look up at pi over 2, cosine of pi over 2 is 0. So I just get 1 there. So notice here that this is decreasing like that. It does not look like it's going to make a circle here. And then if I look this way at pi, that's when this takes its minimum value. So the cosine of pi is -1. So that gives me 2 times -1 is -2, plus 1 is -1. So when I'm looking this way, I'm back to here. But what happened in between here and here? Now this, let's figure that out. So when I'm looking this way, let's say at 120 degrees, or 2 pi over 3, that's when I get a cosine value of negative 1/2. 2 times negative 1/2 plus 1, that's 0. So when I look off that way, that's when I get to 0. And here we have that little bump there. So, and then as I look past that, then I'm going to start to go into some negative values until I get to negative 1. So looking this way, start to get those negatives, and maybe you have an idea now what this looks like. So the other half, it repeats that on the other side, and we get this. Is this a limacon or cardioid or something? I'm not very good at the taxonomy of polar curves. I just know how to make them, which is, I think, more important. So I think we end up with something that looks like this. And real quick reminder, if I can find, oh, there's my calculator over here. Excuse me for a second. You can graph these with your calculator. We're not going to do a whole heck of a lot of that. But just to check our work there, we can go into polar mode. And then our y equals is magically transformed into r equals. And I can put in 2 cosine. When I push the x button, I'm in polar mode, so it chooses that option for me, plus 1. And before I graph it, I need to make sure that I'm in radian mode. I am. And I'm going to go to my window. So it's going to go from 0 to 2 pi with those steps. That's probably okay. I think this is pi over 24, maybe, is the default. Pi over, is that what it was? 0.1, yeah, pi over 24. So that's, a bunch of steps. 12 steps for every pi over 2. If it comes out too jagged, we can just make that smaller. And notice that should remind you of how parametric mode works, and that's a link we'll be making soon. So the x min, I'll make since the maximum of this is positive 3, I'll go from negative 3 to 3 and negative 3 to 3 for the y's also. And there it is. Just what we thought. And if that looks a little funky to you because it's sort of squished in this direction, you can always do zoom square. That squares up the window. All right. There's probably lots of different polar curves that you saw last year, like the ones that make pretty like flower type things like this and so on. And you think about like how would you generate something like that? Well, you have a trig function that's governing how far out you go. Like if you went out and then back in again, out and then back in again, and so on. And if that's happening kind of quickly as you go through those theta values, that's how you get these sorts of shapes. So for example, if you go to your polar graphing mode, think about how would you make a trig function go through those things faster? Well, by putting a multiplier on the theta. So if you did cosine of, say, 3 theta, I was a little off there, started there. It starts here and it goes through, it cycles more. Oh dear. Don't draw on your calculator screen. Not a good idea. And it makes those little petals. And you can make ones with lots of petals if you want by just making them kind of funky values, and make them bigger by putting a number in front, like, how big was that screen? So I could make it like 3, and you could do it with a sine function instead. 3 times, let's say, how about 11 theta? And you get something like that. And if it looks too jagged there, then you can just go in the window and make this step smaller. So I can make it maybe like 0.01 or something like that. That doesn't 0.01. And it'll take a lot longer to do this way, but it'll be prettier if you like flowers, things like that. And eventually it will repeat itself, but if you make it an awkward number like 11, it takes a while for it to repeat itself, and that's why you get the lots of petals on your flower. One other one that I think you should know, just so you can see it, is we did on the other screen r equals cosine theta. What about r equals sine theta? That also makes a circle. And if you think about where you start, when you start off looking in this direction, the sine function is equal to 0. And as you start looking off this way, it gets bigger. And when you get up to pi over 2, that's when it maxes out at 1. And then you keep looking around this way, and it gets smaller again, back to 0, right? So it's like we're taking those values of the sine function that go like this, and we're using those to figure out how far out we're going, and that makes a circle. But notice that the sine circle is up here on the y-axis, and the cosine circle sits down here on the x-axis. All right, that's the basics of polar stuff. And your first assignment is just to try make a few polar graphs, and remember to think polar, which means like you're standing at the origin here, you look out this way, figure out what your r's are, and you imagine what's happening. Am I getting closer to the origin? Am I getting further away as those r's change? Not really that hard to do.